So we discussed about the degeneracy of different levels, energy levels, the rotational energy levels. So this is just some representation. These are just some representation of those degeneracy. So you can see from this figure, this is corresponds to that j equal to 1. When your j value, which is, will have this kind of degeneracy, you will be having 2j plus 1 degeneracy. So that means this value will be, when j equal to 1, this will be equal to 3. So we have three different directions here. So the angular momentum direction, if you consider the rotations, correspondingly we have those angular momentum which is in this direction, it can be in this direction, or it can be in this direction, it can be in this direction. So these three different directions are possible for this angular momentum, and hence you will be having different values correspondingly. So there will be a total of 3 degenerate states for corresponding to this j equal to 1 case. So these are the degeneracy, or what we mean by degeneracy, because if the rotation is like this, and the angular momentum direction will be like this, it will be having same energy as of this rotation, but its angular momentum direction is different. Okay, that you can see from here. We have 0, then we have plus 1, and we have minus 1, corresponding to j equal to 1. So j equal to 1 will be having 0 and plus or minus 1 values. And that will give you different degenerate states with same energy. Energy will be same, but the direction of those rotations which are different. The direction of that angular momentum corresponding to different rotations, they are different, but their energy will be same. So this j equal to 1 have 3 different degeneracies. Similarly, you can find out what are the other possible degeneracies for different states. For example, in this case, we have j equal to 2. So that will be having values states which are 0, plus or minus 1, and plus or minus 2. So that will give you that projection of that angular momentum on that particular, for example, if you consider that axis, this axis, a projection of that particular angular momentum on that axis will give you different values, and that is 0, plus or minus 1, plus or minus 2. And according to that, we will be having different directions or angular momentum direction, and the rotational frequency or rotational energy will be same, but the direction will be different. So with respect to that different directions, we have different degenerate state, which means that they have same energy, but they have different angular momentum directions. So this is the degeneracy in rotational molecules. Okay, when you have that rotational effect, with these are the degeneracy, and this is for j equal to 3 case, j equal to 3. So they will have 2j plus 1 equal to 7. 7 values are possible, so 7 degenerate states are there. So that is nothing but the direction of angular momentum corresponding to those particular rotations. So in this case, it can be rotation will be like this, okay, or it can be like this, or it can be like this. So all these are possible. This kind of rotations are possible in this particular case. So depending on that angular momentum direction, we have different states or with the same energy. They are nothing but the degenerate states. So these are the degenerate states of different states, j equal to 1, 0, 1, 2, 3, etc. Okay, now if you consider another important thing, this is just for the application of when you consider the application, we can find out what is the effect of isotopes on different molecules, effect of isotopes in different molecules. So if you consider that isotopic effect, so this is corresponding to that isotopic effect. Okay, so isotopic effect is nothing but if you replace that uh, the molecule with some of its isotope, some atom, if you replace that with some isotope, then what will be that change? For example, if you consider carbon monoxide, okay, if you replace this carbon monoxide can have, for example, C13 and oxygen 16, or it can also we have C12 and oxygen 16. So both are possible. Okay. So in these two cases, what will be the change in that spectral variation or the output? Okay, when that is carbon 13 and when that is carbon 12. So as you know that B value, which is equal to H by 8 pi square IC. So this I depends on your mass. So this is nothing but I equal to mu R0 square, and this mu is the which is nothing but the reduced mass. So depending on your mass of your atoms in that molecule, that reduced mass will be different. Okay. So in that case, if you have C13, you will be having some particular reduced mass, and if you are having C12, then you will be having different reduced mass. According to that, your moment of inertia will be different. I will be different. So when your I is different, then your V value also is going to be different. And this particular scenario, this is called as isotopic substitution. When you are replacing one atom with its isotope, what will happen to that rotational spectra which is coming out from that sample? Okay, and the relation between those parameters is like B by B dash, if you consider, which will be equal to B is inversely proportional to I, so this will come as I dash by I, and this is nothing but mu dash by mu. So if you take the ratio between those B and B dash, where B dash is the B value with the isotopic substitution, or if you change that mass of any of this atom, or if you replace that atom with some of one of its isotope, then this mass will vary. So that that atom is B dash. Initially, we have, for example, in this case, we have carbon 13, and then we replace that with the carbon 12. We have a different B value. Okay, so if you take that ratios B by B dash, then we'll get we can equate that with I dash by I, because all other things are constant. Whatever you are having this H by square and C, these are constant. So if you take the ratio between I dash and I, that will be same as B by B dash, because B and I are inversely proportional. Then that is again will be equal to mu dash by mu, because R0 square we are treating it as a constant in this particular case. We are considering rigid body rotation. So if you take this R0 square as a constant, then this I dash by I will be equal to mu dash by mu. Or even if you consider this R0 square with substitution of this isotope, or if you are replacing that carbon atom with its isotope, assuming that there is no effect of this R0, it is not going to affect on this R0, because only that mass is going to increase. So in that case, we can say that I dash by I will be equal to mu dash by mu. So if you know this B dash I dash, or mu dash, you can calculate the other parameters, which means that if you know B and B dash, you can calculate what is I dash by I, and you can calculate mu dash by mu. Yeah, then you can calculate what is that mass of that particular uh, atom that you have substituted. So this is called as the isotopic effect or isotope substitution. You substitute some of isotope and find out what is the mass associated with that particular isotope by using this particular relation. So from this you can see that this is carbon monoxide with C13, and this is carbon monoxide with C12. Just I think this one is okay. This one is carbon 13, and this one is carbon 12. So in carbon 12, you can see that this solid line. So this is solid lines. So this solid line represents for carbon 12, which is present in this carbon monoxide. So this is for this particular transitions are for carbon 12 with this oxygen, and this is for carbon 13 with the oxygen. So these are solid lines, and whatever we have here in this diagram, that solid lines for 2b, 4b, 6b, etc. That is corresponding to carbon monoxide with carbon 12 atom, and whatever which is dashed line which is corresponding to this carbon monoxide with the carbon 13. So these are dashed lines. So that will give me the spectra at 2b, 4b, 6b, etc. And that will be at will be denoted as the dashed lines here. So these dashed lines, this is for this carbon 13 with oxygen, and this solid line that is coming as second one, that is carbon 13 with 12, carbon 12. Okay, so there is considerable shift in that p value when you substitute that isotope. When you are changing C12 to C13 for the same carbon monoxide molecule, we can see that the spectra is decreasing. Okay, so initially you have here this 2p position here, it is decreased to here, and then you have here 4p position, it is also decreased to some small value. So that change in that b value, if we found, if you can calculate what is that change. So initially, for example, B you calculate for C12 oxygen, then we can have B dash for C13 and oxygen, that is carbon monoxide with carbon 13. Then there is some difference in this B value, and take that ratio of those B values. Okay, then we will get this is equal to, this can be equated with that I dash by I. From that you can get what is that moment of inertia associated with the carbon 13 oxygen, carbon monoxide with carbon 13. Then that can be equated with your reduced mass mu dash by mu, and you can find out what is this mu dash compared to this. If you know this carbon 12 mass and you know what is mu, and from that you can find out. So mu dash by mu will be equal to some value, let's say x, then mu dash will become x mu. So this mu you know, mu dash, in mu dash you know what is the mass of oxygen, but in this case I'm saying, so you know what is the mass of this oxygen, but you don't know what is the mass of this one. Then you can find out what is that. So mu dash will be nothing but the mass of carbon 13. Carbon 13. I'm just writing. So here mu dash will be mass of carbon 13 into mass of oxygen divided by mass of carbon 13 plus mass of oxygen. So this is your mu dash. And what is mu? mu will be, mu I will write. So mu will be equal to mass of carbon 12 into mass of oxygen divided by mass of carbon 12 into mass of oxygen. So from if you know what is the mass of carbon 12 and mass of oxygen, you will get what is mu, and you substitute some of the isotope of this carbon and find out what is mu dash. That can be given by this ratio mu dash by mu. It can be given by B by B dash from the spectroscopic analysis, and equate that, find out what is this mu dash by mu value, which is equal to B dash by, sorry, B by B dash, which will be equal to X. So multiply this mu with X, you will get mu dash. Okay? Mu dash will be equal to mu times X, and mu dash is nothing but this value, and from that you can find out what is the mass associated with the isotope that you have substituted. This mass you can find out. So this is called as isotopic substitution that we can do for analyzing what is the mass of that isotope. And from this spectral analysis, we can see the change in that p value with respect to this isotopic substitution. And then we discuss about the case of rigid and non-rigid rotator case, what will happen to those energy levels and spectra which is coming out. So it will be looking like this. For rigid rotator, without that vibrational effect, only that rotation we have to consider. In that case, we will be having energy levels as shown here. And for that of non-rigid rotator, the energy levels are shown here, and we can directly see that the energy level is decreased into some smaller value. So when we go higher J values, we can very clearly see the decreasing of those energy levels. But in the lower value of J, that will be very small. The effect will be small, but it is still there. Okay, because that J values, you have that B, 2B into, or if you consider that energy level, it will come as B into J into J plus 1. We are considering the energy that is absolute. So this is B into J plus 1 minus D into J square into J plus 1 square. I think that's right, right? Is that? Yes, J square into J plus 1 square. So in that case, we'll be having that decreasing of energy level. But when you consider this J value, which is suppose some 1, 2, 3, so this effect will be small. This D is small, so multiplication of some, for example, if you substitute 2 here, then 4 times 4 plus 1 square. So 4 times 5 square will come, so it is around 100. The value is around 100. So if you say that say 100D here, so it is small. But when you go for higher J values, for example 10, so because if you are having D, for example D equal to 0.1, you have to multiply this with 100, then it will come some 10. Okay, so this value is smaller, especially when it is some 0.001. This will not make much difference. When the D value is very small, this will not take much difference, and the value of those energy levels will be almost similar to B into J plus 1. But when you consider, for example, J equal to 10 case, then you have to consider 10 square here, so it will come 100 into, in this case I'm saying, so J square will become 100, then J plus 1 square is 101 square, sorry, 10, 11 square will come, okay? 10 plus 1 square. So this will become a very high value, and multiplying that value with this D, that will give that will give somewhat considerable amount, and that will cause considerable decrease in energy level. Okay, so when we go for higher J values, even though D equal to some 0.001, this has to be multiplied with some large value. When you go for example, for J equal to some 2, we have seen it is 100. Will come as 4 here, 4 into, we'll just say, sorry, this is J equal to 2. This will come as 2 plus 1, right? 2 plus 1, so this is 3 only. Okay, so it is 9 into J square is 4, so 4 times 9 will come, so this is around 36. So this is coming around 36. So this will not be having much effect on that when J equal to 2. But when you consider J equal to 10, then this will become, when this I'm talking about this quantity. This is not that. This quantity will become like this. This quantity will be equal to 1001 into 10 raised to, sorry, into 36 when your J equal to 2. When J equal to 10, when J equal to 10, it will become 0.001 into, it will become 10. This will become, J square will become 100 into J plus 1 square will become 11 square. So this will become considerable value now, because if you multiply 100 into 0.001 itself, it will become considerable to this value, B into J into J plus 1. Okay, and then we have 11 square also. So that will become considerable value as compared to this B into J plus 1. Then the effect of that on these energy levels will be higher. So we can clearly see considerable decrease of the energy level when we go for higher J values for the case of non-rigid rotate. Okay. So that is the energy level shift because of that vibrational effects. But when you consider this spectra, which is coming out from these transitions of these energy levels, we can see a considerably uh, equal width spectra for rigid rotators. We can see from here, they are having same width with the 2b, of width of 2b. If you take any of the spectral line, the separation will be 2b. So they are having EQ spaced spectral lines. And if you consider that of the non-rigid rotator case, that is the second one. This is for rigid rotator case. This is for rigid, and this is for non-rigid case. For non-rigid case also, you can see the spectral line is continuously decreasing when we go for higher values, higher J values. Okay, so this one starts decrease somewhere here. Considerable decrease will happen when you go for higher J values. So that's all about the rigid and non-rigid rotator case. Also, you can see the variations of those different energy. For example, this is 20B line here. That will be shifted to here. For non-rigid, okay, that is here, rigid and non-rigid case. Okay, so that's what we have discussed in the last section. Now we will discuss what will be the action of this particular rotational effects when you consider a linear polyatomic molecule. For the case of linear polyatomic molecule, what will happen? So when you consider linear polyatomic molecule, whatever we have discussed is for example, carbon monoxide, which is a linear diatomic molecule. Now what will happen if you are considering linear polyatomic molecule, which means that the number of atoms are more than 2. Polyatomic molecule. Diatomic molecule also will be contributing this. But in the case of polyatomic molecule, what we mean by that is that we have different number of atoms, more than that of 2. Okay. Then we have, for example, consider example for this type of molecules are HCN, or you can take OCS. This is hydrogen cyanide. This is hydrogen cyanide. Then we have here, this is carbonyl sulfide. So these are linear polyatomic, which means that we have 3 different atoms in this particular molecule. So they are not diatomic molecules. So when what happens if it is linear polyatomic molecule, for example, triatomic or more than that, in that particular case, what will happen? The moment of inertia conditions will be same. Okay, for example, as we discussed in the case of linear case, for linear case, moment of inertia condition, that condition will be same, which means that IA, if you consider IA will be equal to IB, or we'll treat IA as small, right? So that fashion itself. So in conventional way, we will write it as IB equal to IC, which is not equal to IA, and IA equal to 0. This is for linear case. So same condition will be valid for the case of polyatomic molecule also, as the same condition of that of diatomic molecule. This condition is same for any linear molecule. This condition will be same. So that the transition also will be delta J will be equal to plus or minus 1. That is the transition rule, the selection rule. For that transition, delta J will be equal to plus or minus 1. And also mu bar, if you consider, mu bar will be equal to 2b into J plus 1, 2b into J plus 1 minus 4d into A plus 1 cube. So all these things will be same. All these things are same. I think I have, whether I have written that mu bar here. Last section also. Yes, this difference is EJ plus 1 minus EJ. This difference we called as mu bar, right? Yes, in terms of B, yes. So this is your mu bar, okay? So that difference between those energy level in terms of centimeter inverse, that is mu bar. So that mu bar also will be same for polyatomic linear molecule. For all linear molecule, it will be same. Okay. Now, where the change will happen? Where will be that change? If it is diatomic molecule, it will be having some spectra, some rotational spectra associated with that molecule. If it is polyatomic, for example, triatomic molecule, what will be the change that we can expect? If all these conditions are same, then where that change will happen? The change will happen in case of in terms of moment of inertia. Moment of inertia for the end-to-end rotation of this linear molecule, when we have more than 2 atoms, which will be greater than that of diatomic molecule. Okay? So the point here is that the moment of inertia, for the end-to-end end-to-end rotation will be higher for this. For example, if you are considering triatomic molecule or any higher molecules, so we can, in general, we can say that linear polyatomic molecule. And in bracket, you can say the number of atoms greater than 2. So end-to-end rotation, moment of inertia for the end-to-end rotation will be higher for linear polyatomic molecule as compared to diatomic molecule. Diatomic, you can write it as linear diatomic molecule. Okay. So hence B value, B will be smaller. B will be smaller for polyatomic molecules. So whatever we are saying, polyatomic or diatomic, which is linear polyatomic molecule and linear diatomic molecules. Okay. As you know that this, for example, if you consider a situation like this, if you are having atom here, another atom Y here, and another atom Z this point, with your center of mass at this point, or the gravity is at this point, center of gravity at this point. So if you consider a situation like this, for example, in the case of a triatomic molecule, we are talking about the end-to-end rotation, which means that if you are considering this axis, this is the principal axis of this molecule, or the molecular axis, we say. Apart from that, if you are considering that end-to-end rotation like this, okay, we have moment of inertia which is larger. Why it is larger? Because we have 3 different atoms, so the mass will be larger, because we have to consider 3 different atoms. Okay? So in this case, we'll be having 3 different atoms. For example, if you're considering triatomic molecule, and we have to consider mr square corresponding to each of these atoms. That is the moment of inertia associated with each of these atoms. Then we consider those moment of inertia corresponding to each of these atoms at different axes, IB and that is B and C, then IB and IC will be larger in this case, because we have number of atoms which are larger. Okay, so correspondingly we will be having moment of inertia which is higher in the case of linear polyatomic molecules. And as you know, your B value, which is inversely proportional to the moment of inertia, hence B will be higher. B will be smaller. Will be smaller for polyatomic molecule, because your I value, which is moment of inertia, is higher for polyatomic molecule. Okay, moment of inertia is higher for polyatomic molecule. Hence, we have lower B value for polyatomic molecules as compared to diatomic molecules. Okay, our B value will be smaller for the polyatomic molecule. So when the number of atoms in your linear molecule is increasing, then your B value will get reduced, or the separation between those levels. If you consider this B value, sorry, in this case, in the rotation, if you are considering only that's rotation, then we have that separations like this. Okay. and some first one is 2b, then 4b, then 6b, etc. will be there. And but when you consider the next one, which means that so for example, this is case of diatomic molecule, and the next one will be having same kind of spectra, but the separation between these two, that will be smaller. So they are equispaced. They are equispaced because we are considering only that rotational effect here. When you consider only that rotational effect, they will be equispaced, but that b value will be different. Okay, which means that if you are considering here these two, you'll be having 2b difference between these two spectral lines. But when you consider these two, you'll be having 2b dash. Okay, and this b dash will be smaller than that b for the case of polyatomic molecule, polyatomic linear molecule. So in this case, we are considering, for example, if you are considering triatomic molecule, also or any other higher order or a number of atoms which are higher case also, we will having b dash which is smaller than b, and this b is for diatomic molecule. Why it is coming? Because moment of inertia in polyatomic molecule case will be higher as compared to the diatomic molecule case. And if you really want to calculate what will be this moment of inertia for this case, for example, and for this I will consider the separation between these two, this x and y, I will take it as rxy, separation between these two. This is rx y, and separation between these two, that is y and z, that is ryz, and separation of y from the center of mass, that I will take it as small r. Okay, then moment of inertia corresponding to this triatomic molecule I will be equal to mx, that is mass of the first atom, that is atom x, that has to be multiplied with the rxy plus r, because the total distance up to this center of gravity is rxy plus r. Okay, so that is this distance, perpendicular distance, or distance from that center of mass to this x atom. So this square plus the second atom is my, and the distance from that center of gravity is r. So I will multiply with that r square, plus the third atom is mz, has to be multiplied with the subtraction of that from the center of gravity is nothing but ryz minus r square. So this is the moment of inertia associated with that particular molecule, triatomic molecule. And if you are applying that center of gravity, considering that center of gravity, then we have this particular condition. We're considering that as a center of gravity. Then we have mx multiplied with rxy plus r plus my multiplied with r, y multiplied with r. This should be equal to mz multiplied with ryz minus r. So this is the condition when we have that center of gravity. At that point, whatever mass into distance which is coming or balancing at that point should be equal on both sides. Okay, so in this side we have mass which is z. If you consider this as your center of gravity, from that center of gravity, this side we have only one mass. Okay, so that mass with this separation distance from that mass from this center of gravity, which it should be equal to the mass times separation of each of these masses, which is on the left hand side. Then only they will be balanced to each other, and this point we'll get the center of gravity, or all the mass will be concentrated at that point. So with that center of mass, center of gravity concept, we can write it like this: m into rxy plus r plus my into r equal to mz into ryz minus r. Okay, so by using this particular expression, we can find out what is the value of r. That will come as mz times ryz minus mx times rxy, and this has to be divided with capital M, and where capital M is equal to mx plus my plus mz. So you reduce this expression in such a way that you have to find out what is the value of r, then we'll get r equal to mz ryz minus mx rxy divided by m, and capital M is nothing but mx plus my plus mz. Now you substitute that for r, then your moment of inertia I will be equal to mx my, okay, mx my, because the first value moment of inertia you substitute here for r, then it will come as mx my rxy square plus my mz, this is ryz square, plus mx my into rxy plus ryz square, and this has to be divided with that mx plus y plus mz. So substitute value of r in this expression of moment of inertia, and then you will get the total moment of inertia of this triatomic molecule like this. So this is how we will calculate moment of inertia of triatomic molecule. For diatomic molecule, it is easy. We have to just consider those masses. We already did that. Mu r square you had to consider. For diatomic molecule, it will come as mu. But for triatomic molecule, you have this kind of expression. For any higher uh, number of molecule, if it is present as a linear fashion, then linear polyatomic molecule with the number of molecules is more than 3, then we have to look for moment of inertia of that system in the same manner. Okay, so we'll be having some complicated moment of inertia equations when you go for higher number of molecule with higher number of atoms. Okay, so this is the moment of inertia for this triatomic molecule, and from this we can easily see that the moment of inertia associated with the polyatomic molecules will be higher as compared to that of the diatomic molecule. Hence the b value of the polyatomic molecules or the molecule with higher number of atoms will be smaller as compared to the diatomic. Okay, now what will happen for the case of symmetric top molecule? So we have discussed about diatomic molecule, we have discussed about polyatomic diatomic molecule as well as diatomic molecules. Now what will happen if you are having symmetric top molecule? Apart from linear molecule, if it is symmetric top molecule, what will happen? So for the case of symmetric molecule, we have two different scenario. One is the prolate nature or prolate molecule. Okay, and second one is the oblate molecule. Okay, so for these two molecule, what will be the change? So I will just discuss that, and I will complete this. So I will just discuss that part also here, and I will look into that deeply in the next section. So if you are considering symmetric top molecule, so you have symmetric top molecule. So in the case of symmetric top molecule, as we said, for symmetric top molecule, there will be two independent moment of inertia, and therefore there are two directions of rotations in which the molecule might absorb or emit energy. So in this case, we have two for symmetric top molecule. For symmetric top, I will just write it as some points. So for symmetric top molecule, we have two independent moment of inertia. And therefore, there will be two different directions of rotations in which the molecule may, so this will give two different, or we can say kind of rotations, or a type of rotations. Rotation. Okay, two different types of rotations are possible. So by using these two different types of rotations, by which the molecule may absorb or emit radiation. So this radiation is microwave radiation. So this may be microwave. This will be in the microwave range. So these are microwave radiation. So two different types of rotations are possible. What it means, you have the for symmetric top molecule, you have two different moment of inertias. For example, for the case of prolate case, we have IA which is less than IB, this is equal to IC. So this is for prolate that we discussed in the last section. And then we have IC which is higher than IA which is equal to IB. This is for the oblate case. I will discuss that oblate and prolate geometry in the next section. So we have to consider the inverse of that moment of inertia. I think that have to be drawn like that. So that we'll discuss in the next section. So we have two different kind of symmetric molecule. One is prolate and another one is oblate. And in the case of prolate, we have IA which is less than IB equal to IC. And in the oblate case, we have IC which is greater than IA which is equal to IB. So what that means, which means that we have IA as well as IB or IC. So we have two different moment of inertia here. One is IA and another one is IA, IB or IC. Or if you consider oblate, we have IC, then IA or IB. In the case of linear molecule, what is the difference? In the case of linear molecule, we have IA which is equal to 0 and then IB equal to IC. So only one moment of inertia is there, or only one kind of rotation is there. IA is 0, IB is equal to IC. So we can take IB, either IB or IC. So only one type of moment of inertia or one kind of rotation is there. Only that we have to consider because IA equal to 0. The other moment of inertia part is 0. But in this case, we have IA, which is also there, which is smaller than IB and IC, but still it is there. And we also have IB and IC. So either one of these we can take, IB or IC, and also we have to consider IA, which is not equal to 0. So in this particular case, we have two different moment of inertia, which means that we have two different type of rotations for these symmetric top molecules. So since there are two different types of rotations which are there, we have to consider two different quantum numbers. Okay, so there are two different type or kind of rotations. It results in two different quantum numbers. Two different quantum numbers. So in the linear case, we have only considered single quantum number, rotational quantum number, which is nothing but that J, single quantum number, rotational quantum number, which is J. But in this case, we have two different types of rotations. So we have to consider two different quantum numbers. Okay. So if you calculate the energy, and if you say what are the different rotations, these two different rotations. One is the rotation about the molecular symmetric axis, rotation about the molecular symmetric axis, and second one is about the rotation perpendicular to the molecular symmetric axis, perpendicular to molecular symmetric axis. What is this molecular symmetric axis? This axis is the axis by which the molecule will be symmetric about that axis. Okay. So, for example, if you consider a symmetric top molecule, you consider any symmetric top molecule. For example, if we consider uh, in the previous class, we considered as an example that ClCH3. So, if you draw that one, just check that which example. I think it was CH3, right? CH3F. So it is like F here. Then we have this C. Then we have those H. Something like this. Okay, so if you are considering an axis, with respect to that axis, the molecule has to be symmetric. Then if you consider, for example, this axis, I think if you consider this particular axis, the molecule will be symmetric about that axis. This molecule is symmetric about that axis. And in that case, you have rotation. Two different rotations are possible here. One rotation is that this kind of rotation. That is about that axis, symmetric axis. That is possible. Okay. In that case, these hydrogen atoms are rotating. These hydrogen atoms are rotating like this about that axis. So they will be rotating. Another possible rotation is that this entire hydrogen atom, just this rotation. So this is one rotation that is about that axis, symmetric axis, molecular symmetry axis. Another rotation which is possible is that this entire hydrogen atom, which are rotating perpendicular to this axis. Okay, so that rotation is like this, and this fluorine atom will be rotating from that position to this. So that rotation will be like this. So it will be perpendicular to this axis, rotation perpendicular to this axis, this molecular symmetric axis. So the molecule will be rotating like this. The entire molecule is rotating like this. So that is also possible. So two different kind of rotations are possible, and corresponding to these two different rotations, we have two different moment of inertias. Okay, so if you are considering IB and IC, they will be same. So these two different rotations, if you consider to in different axes, then we already discussed those things in when we discussed about that symmetric of molecules. They will be same for IB and IC, but there are the two different kind of rotation for symmetric top molecules. One is about the axis, that is this one. About the axis, it can rotate like this. So the fluorine's position will be fixed, and hydrogen will be rotating about that axis. But in the second case, the rotation perpendicular to that molecular symmetric axis. So the entire molecule will be rotating like this about that center of mass. For example, if you are considering this center of mass or center of gravity of that this particular molecule, let's consider it is here. I think it will be there. If you consider that the center of gravity position is at that point, just above that carbon atom. For example, if it is here, over here, then with respect to that center of mass, the entire molecule will be rotating like this. So the fluorine and hydrogen, all those molecules will be rotating about that center of mass like this. So that is possible. So these two different kinds of rotations are possible in all the symmetric top molecules. So since there are two different molecules, different types of rotations which are possible, we need two different quantum numbers. In the case of linear molecule, if you consider that carbon monoxide case or any other molecule which is linear in nature, then in that case, if you consider, for example, that carbon monoxide case, we have carbon here, oxygen here, which are separated by their bond length. Okay, so in this case, the only possibility is that the rotation is like this. This rotation is possible. Okay, if we are considering the center of mass in some position, uh, let's say this is oxygen, which is near to that oxygen. And if you are considering it can rotate like this. Okay, it will not be having same fashion, because when the carbon reaches, when the oxygen reaches this point, carbon will be somewhere here. I'll just draw it in a different color. So when you are considering rotation in the next moment, when the oxygen reaches on the other side, carbon will be somewhere here. So the path will be like this. So it is not exactly circular. This shape will be like this. It will be shifting. Okay. So anyway, that rotation will be like this. One possible rotation, and this is about one particular axis. For example, if you consider that for this axis, which is coming out of the screen, out of your screen, this rotation, that is possible. And another axis with the same rotation, which is this axis. So if I am saying, considering same molecule carbon monoxide, consider same molecule. If you consider carbon monoxide, and another possibility is that you have one axis perpendicular like this. So it is in that plane. So the rotation can happen like this. But these two rotations are same, and moment of inertia corresponding to these two are same. That's why we have IB equal to IC for linear case, IB equal to IC, and which is not equal to IA. What is IA? IA is about that uh, principal axis or symmetric axis of that molecule. So in the principal axis, if you consider about this axis, the moment of inertia will be equal to 0, because both carbon and oxygen are coming in that axis. So the perpendicular distance, if you consider of this molecule, that will be 0. So moment of inertia about this axis is 0, That's why we are getting IA equal to 0 in this case. So only one type of rotation is possible in this case. So we only need one quantum number, which is J. But in this case, symmetric top molecule, we have two different kind of rotation. So we need two different quantum numbers, and we take it as J and K. So we'll consider two different quantum numbers in case of symmetric top molecules. Now, if you calculate the energy after doing after solving that Schrodinger equation on those things, quantum chemistry, if you consider, and consequently after that solution, we will get the energy associated with this particular case. So solution of Schrodinger equation corresponding to this particular system, that will give you energy E j comma k, because we need two quantum numbers, that will be equal to h square by 8 pi square I j into j plus 1 plus h square by 8 pi square I minus h square by 8 pi square I. This times we have here k square, this much of joules. So remember one more thing, I have put only I here. This first I is IB, and that is equal to IA. Okay, when I'm considering this is for the case of prolate, I'm considering this is for prolate case. Similarly, you have to write for oblate also. So in prolate case, we have IB equal to IC, which is not equal to IA, and IA is smaller than this IB and IC. So this IB will come as first one, and then we have IA, which is smaller. So this is IA. Then we have IB. This one is IB. So either IB or IC you can consider here, because both of them are same. So this can be IB or IC. This one is, this can be IB or IC. So this will be h square by 8 pi square IB j into j plus 1 plus h square by 8 pi square IA minus h square by 8 pi square IB into k square, this much of joules. So if you want to calculate what is this energy in terms of wave number, that is epsilon j comma k, then that will come as B times j into j plus 1, okay, plus next one is IA. Okay, so I will replace that with A minus B. So what is this B? B is nothing but h square by 8 pi square. In this case, it is IB times C. And what will be that A? A is nothing but h square by 8 pi square I. Here it is IA into C. And this is nothing but EJK. As you might be knowing, EK by C will be given by epsilon JK. And that is nothing but B into J plus 1, where B is h square by 8 pi square IBC, A equal to h square by 8 pi square IAC. In the same manner, if you calculate this for oblate case, so this is for prolate case, for prolate, where you have IB equal to IC, and which is larger than IA. And for case of oblate case, similarly, if you calculate for the case of oblate, then we'll be having epsilon j, which is equal to B into j plus 1, plus here we'll be having C minus B. Instead of A minus B, we have C minus B times K square, where what will be the C? C will be equal to h square by 8 pi square I C into C. Okay, so these are the energy for the case of prolate and oblate. So this is for oblate case. And remember that we have here A minus B, here we have C minus B. And it has some importance that I will discuss in the following explanation. So this is the condition for Proiet and oblate energy levels. Okay. So the A, if you consider that A value, the molecular axis, this is corresponding to that molecular axis, and B is the direction in the plane of the paper uh, through that the center of gravity and perpendicular to the axis A. That we already we discussed those things when we discussed the symmetric of how these axes are coming. Now we will just consider, so that one is about that symmetric axis. So A will be coming about that symmetric axis. As you know, you draw that CH, this we already know. That's why I'm not going to discuss these things. So this is F. So if you take that axis, this will be your A. That A will be smaller with respect to that A. If you consider that rotation, that will be smaller as compared to the other rotation, because in that rotation we have 3 hydrogen and 1 fluorine. The second rotation I'm saying. So for IC and IB we have rotation like this. So in that case we have 3 hydrogen as well as this fluorine which is rotating about that center of mass. But in this case, when you are considering A about this axis, that is the molecular symmetric axis. And about that, if you are considering the rotation is rotation is like this, and only that 3 hydrogens which are rotating, so moment of inertia corresponding to that particular case will be smaller, corresponding to as compared to these other 2 rotational motion. One is this, and other one will come in the other. If you consider this axis, one is this axis, and another one is this axis. So rotation also coming this way. So entire molecule will rotate. So in that 2 cases, we have all the atom, fluorine and 3 hydrogen rotating. So mass is larger and moment of inertia will be larger. But in the case of this A axis, about that molecular axis, the rotation is only these 3 hydrogens which are rotating. So mass is smaller. So moment of inertia will be smaller in that case. Okay. Okay, so these quantum numbers J will be, you can take values 0, 1, 2, 3, etc. And this K can take values 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. And this is up to plus or minus J. Okay, so J represents total angular molecule, and K represents the projection of the total angular momentum upon the molecular symmetry axis. So J is the total angular momentum, because of all those rotations. So this is total angular momentum, and K is the projection of this total angular momentum, total angular momentum upon the molecular, on the molecular axis or molecular symmetric axis. So J represents that angular momentum, total angular momentum, and K is the projection of that total angular momentum. As we discussed in the previous section, also we are having one particular J value. Let's say this is your J value. So for example, J equal to 1. Then we have different directions possible, and these directions are, so this is 0, and here we have plus 1, and here we have minus 1. They are the projection of this particular total angular momentum of these different directions to that principal axis. Okay, so if you consider the axis of symmetric axis of that molecule is in this direction, projection of this uh, total angular momentum on that axis will give you k values. So for j equal to 1, these are the k values. These are the k values. They will give you the projection of this total angular momentum, and j is the total angular momentum. So we have k equal to 0 plus or minus 1 plus or minus 2 plus or minus 3 up to plus or minus j. Now what will be the energy level difference? It is an important thing. For the case of prolate, as you know, for the case of prolate, we have IB. For prolate, we have IB which is greater than IA. Similarly, IC also greater than IA because IB equal to IC. Then that will give me B value which is smaller than A, because this B is inversely proportional to IB. This A is inversely proportional to IA. If IB is larger than IA, my B value will be smaller than A. Okay? And from that, A minus B into K square, A minus B into K square, this term is positive because my A value is higher than B. Consider oblate case, considering that oblate case, then we have this IC, or we can say IB or IA, both you can take because IB equal to IA in this case. So this IB is smaller than IC for oblate case. You can cross check that. And then your B, in this case, your B is greater than C. Okay, because your IB is smaller, so B will be higher because B is inversely proportional to IB as compared to C. So B will be larger. So this is coming from that equation B equal to h square by h by 8 pi square I B into C. So if IB is smaller, then B is larger. So if IB is smaller than IC, then I can have B which is larger than C. Then it will give you that C minus B in that previous equation of energy, C minus B into K square, this will be equal to negative, which is negative. This is very important. So in the case of prolate, that second quantum numbers effect or the rotation effect, second type of rotation effect will cause a positive change, or it will increase the energy level. But in the case of oblate case, it will decrease the energy level. Okay, as you can see from this energy level calculations, you can see from here this is A minus B into K square. So this is plus A minus B into K square. So whatever we are having with that about that axis, that rotational case, if you are considering, and then plus that energy level plus some additional energy will come in this case because A minus B is positive here because A is greater than B. But in this case, we have the same rotation here. But in this case, we have C minus B, which is negative quantity because B is larger than C, or C is smaller than B. So this quantity will become negative. So the total energy will get reduced. So B into J plus 1 minus some quantity will come because of this rotation. Okay. So in the case of oblate, the energy level decreases because of the presence of that second rotation. But in the case of prolate, its energy will be increased with that presence of that second rotation or second quantum number. So if you draw that, then we can draw it like for J equal to 0, we have first energy level J equal to 0. Then we have J equal to 1. For J equal to 1, we have two different energy levels. One is for k equal to 0 and k equal to 1. So I am just drawing it here first. I will just draw it here, two energy levels, and I will explain that later. Then we have j equal to 2. We have three different energy levels. Let's close this. Consider j equal to 3. Then we have again different energy levels. So these two are very close to each other. The next one will come here. One more. So let's take this somewhere. Taking this magnitude of k in this section. So these are j values. First I wrote j values equal to 0. Then I am talking about magnitude of k. In this case, this will be equal to 0. And then I'm having magnitude of say k equal to 0 or 1. Because for 1, we are having k equal to plus 1, 0, and minus 1. So if you take magnitude of this, we will be having 0 and 1 only. Minus 1 will also come with this one. So this state is degenerate. This one is degenerate. There is 1 and plus or minus 1 will come. And again, we have all these are degenerate as compared to this rotational energy quantum number, because we have j equal to 1, and that is degenerated into three different levels. You can see 2j plus 1 is the degeneracy, 2 into 1 plus 1, that is 3. So we have taken only that magnitude of k here. So this is 0, this is 1, this level is also having that minus 1. Both are. And then we have 2 here. Then we have k value which is 0, 1, 2. Actually, the k value will come as 0 plus or minus 1 plus or minus 2. We are considering only the magnitude of that k value. So this one is also, there is 1 and minus 1 in this level. This level we have 2 and minus 2. Similarly, if you draw the energy level corresponding to these 3, then we have 0, 1, 2, and 3. And in this case, it is plus or minus 3, plus or minus 2 plus 1. So we are considering only that magnitude. That is the case for prolate. Okay, so from that 0 level, okay, from that 0 level, it is increasing. When it is become 1, it is increasing. 2, 1, and 2, it is going to above this 0 level. So if it is only 0, that is corresponding to j equal to 0, 1, 2, 3 levels. Okay, there is no k, which means that when k equal to 0, from this expression you can see, just show you this expression. So if you put k equal to 0 here, you do not have that second rotation, which means that you do not have that second rotation. So if you put k equal to 0 here, then you have only this b into j plus 1. That is nothing but the energy level correspond to rotational case of linear molecule. Okay, but when you are having k value here, then that will result, it may be plus or minus depending on the c minus b, whether it is positive or negative. Depending on that, it will be decreasing or increasing. Okay, so when k equal to 0, which means that you have only this energy level, which means that it is equal to that linear case. When k equal to 1, depending on that value of this c minus b, it will be different. Okay, we do not have to consider k equal to plus or minus 1, because k is square we have to consider. So even if you put to plus 1 or minus 1, the energy level will be same. Okay, then if you put k equal to 0, then you will get linear molecules rotational energy level. That is same. So these k equal to 0 levels, these are for linear case. We just use some other color, show that. So this j equal to 0, this level are equal to that of that linear case, j equal to 0 in all cases, which are equal to that linear case. But when your k is different from that, k equal to k not equal to 0, for example, k equal to 1, 2, 3, etc., plus or minus 1, plus or minus 2, plus or minus 3, then because of that additional rotation will come in symmetric top molecule, and we have other energy levels. And in the case of prolate, it will be increasing. That energy level will be increasing with presence of K. But in the case of oblate, as we discussed earlier, that C minus B will be negative, and the whatever that you are getting from linear energy, which will be decreased with the presence of the second rotation in the case of oblate. So this is case of prolate. This is case of prolate. And in the case of oblate, we have different energy levels. We'll draw that 0 first. The 0 level will be the same. So K is also 0, J also 0. And then we have that 0 level here. And from this 0 level, the next level will be less than that in the case of oblate. And if you consider the second one, you have 0 level here. The next level will be less than that. It will come somewhere here. And if you consider third one, your 0 level is somewhere here. The next level comes here. And 2 will come here somewhere. 3 will come somewhere here. So from the base 0, so this is K, this is equal to 0, this is K equal to 0 and 1, K equal to, sorry, this one will be in the opposite way. Discussed. So this one will be 0 and this one will be 1. This one is, in this case, it will be 0 here, 1 here, 2 here. Then this case is 0, 1. Because when that quantum number K comes, it will decrease the energy level when K equal to 0 as compared to that K equal to 0. So the energy level will be like this for the case of prolate. This is for, sorry, oblate. So these are the energy levels, whatever, oh, sorry about that. Should be, because it is coming 1. This is 1. And 0, when K equal to 0, we have the energy level which is same as that of linear case. These are same as of that of linear case. So if you are considering comparing that symmetric top molecule with the linear case, we have additional energy levels which is coming from that additional rotation, and which will be like this, okay, and so on. So in the case of prolate and oblate, these energy levels will be different. And the transition also occurs between these energy levels. Okay, and that transition selection rule, I will just write that selection rule here. So selection rules are delta J equal to plus or minus 1, and delta K should be equal to 0. This is the selection rule for transition in case of symmetric top molecule. We will discuss more about it in the next class. So these are the important points that we have to cover in the symmetric top molecule. In the case of prolate and in the case of oblate, there is difference in energy level diagram, in energy levels, and how it will be in the case of prolate and oblate that we have discussed.